Okay, so this is a review, not everything that you need to know or to teach you everything you need to know, to explain everything. This is just a review of work energy. I don't want it to be super long, but it'll probably be too long anyway. So let's just imagine the following situation as an introduction to remember where we should be. If I have this ball of mass m and I drop it and it goes from position 1 to position 2, a drop height of h, then how fast is it going down at the bottom? V2 equals the magnitude. So you could use the momentum principle. The momentum principle says that the net force is delta P over delta T. So if I want to find the change momentum, that'd be delta P equals F net delta T. That's the momentum principle. Okay. There's another principle that we can use, and it's called the work energy principle. Work energy principle says the following: the work done on a system, in this case I'll be the system of just the ball, is going to be equal to the change in energy of the system. That's it. Okay, well, what's energy and what's work? If the most basic definition of energy would be kinetic energy, and there's other ways to explain this. But let's just say energy. We have kinetic energy is 1/2 mv squared, and that's the change in kinetic energy. Now, what about work? Work, if the force is constant over a constant path, then this would be F dot delta R. Okay, so see, we're causing a lot of problems here, right? Because now we have this dot product, and I should explain the dot product. So let me get to these are really important. And the dot product isn't as super important because it's not really physics, but let's just say I have two vectors, A, and it has the components AX, AY, AZ. And then I have the vector B, and it's BX, BY, BZ. Then A dot B is going to be, it's a way to operate two vectors. It's not multiplication, okay, because you can't multiply vectors. It's a different operation. And in this operation, we get a scalar value based on these two vectors. To get that scalar value, it's defined as the product of the x components plus the product of the y components plus the product of the z components. So that'd be ax times bx plus ay times by plus az times bz. That's the dot product. And you'll notice that you can't have a positive or negative vector. We wouldn't say that, but the components can be positive or negative. So when I multiply and add this up, it's positive. It's possible I could get 0. It's possible I could get a negative number. It's possible I could get a positive number, but there'd be a scalar. Now, there's actually another definition that is sometimes useful. A dot B is going to be equal to the magnitude of A, which is a positive number, times the magnitude of B, which is a positive scalar number too, times cosine of theta, where theta is the angle between the two vectors. And so cosine theta could be anywhere from -1 to 1. So again, you can get 0 positive or negative number for the dot product. So those are two ways to do that. In this case, we're doing this with F and delta R. Okay. So if I did that up here, I would say, well, what force is acting on my system of just a ball? It would be the gravitational force, mg, and then delta R, so I'd have F equals mg. Delta R would go from position 1 to position 2, so that would be the vector 0, negative h, 0, right? Because it's moving down that way. And in fact, I can write this as F as m, let's say, right, 0, negative mg, 0, right? Because that's the y component of the force is negative mg, but that's just m. So then work equals F dot delta R. So it's going to be 0 times 0 plus negative h times negative mg, so I get mgh, plus 0 times 0. And that's going to be equal to the change in kinetic energy, which is K final, which is 1/2 mv2 squared minus the initial 1/2 m0 squared. So now I could solve for v2. The m's cancel, and I get v2 equals the square root of 2gh. And if you did this using the momentum principle, you get the same thing, except there is one really big difference. And that is that this actually gives you the vector momentum and the vector velocity at the end. This gives you the scalar velocity. It actually doesn't say which way it's going. Okay, it is possible that it could end up at the same spot moving up with the same speed. And I'll show you that in a second. Okay, so that's your very basic work energy principle. Now, what about conservative forces? Conservative. So suppose I have the same situation. And I calculate, I did the work energy principle there. Now let's say I take this path. It's in blue, it's a blue path. It goes like this, and then it goes like that, and then it goes like that. So in this case, I need to find the work, but I have 3 different paths, so I need to do the work 3 times. So I could say the work is going to be, the force is the same in each case, right? But the path is different. So I can say the work is work along this path, which is going to be the vector mg time dot delta r1, that's a vector, plus mg dot delta r2, which is, this is delta r1, delta r2, delta r3, delta r3. So if I look at delta r1, let's say this is distance s. It's going to be the vector s0, 0. And so now when I take this dot that gravitational force, the gravitational force only has a y component. This only has an x component. So I would get mg dot r delta r1 is going to be s times 0 plus negative mg times 0 plus 0 equals 0. So the work done on this path is 0. You can also think of that as the force is down and the displacement is perpendicular to that, so the angle between them is 90 degrees. Cosine 90 is 0. And then if I do this, I get the work done along this path. I get mgh, just like before. I already did that problem. And then along this path, I get the work is 0. Again, because it's perpendicular, you can do it a lot of different ways. So the work done along this path and this path straight down are the same. So it doesn't really matter what path you take. And in fact, you could even do something like, and I have a problem where I did this. I'll try to find it. The circular path, the work done along that circular path is difficult to calculate, but you get the same thing. It does not matter which way you go. If that's the case, then I can go over here. Work is a change in energy, and I can subtract work from both sides, and I get 0 equals delta E, well this is delta K, let's call that K, minus the work, and I'm going to call minus the work delta U. So delta U equals negative work equals negative F dot delta R. Because once I do that integral, I don't need to do it every time. I can just move it to the other side, and I can call that a potential energy. Now, if I do that, if I want, so I can do 2 things. I could say system of the ball, and then work equals a change in kinetic energy, and I'd have work done by gravity. Or I could do system of the ball plus the earth, and then work equals delta K plus delta U. And so up here, since delta U is opposite of work, I can just say U equals mgy, the change in potential. And I'm trying to think, yeah, that's delta. That's y in general. Okay, but the delta U is negative mg. So this would, in this case, there'd be 0 work done. If I had the ball plus the earth as a system, I'd have 0 work, but I would have a change in gravitational potential. If I say there is just the ball in the system, I would have work done by gravity. So you can either do it, you can do it either way. I can have work done by gravity or change in gravitational potential energy. You can't have it both ways. Okay, you can't have it both ways. So with that, there are some other forces that do work that don't depend on the path. And we can make these potentials. So I have gravitational force and a gravitational potential energy. I have the real gravitational, negative G m1 m2 over r. Now again, this is the potential with respect to infinity. You really want to always have changes in potential energy. That's what shows up in this equation right here. It's a change in potential energy that shows up. I have the potential due to, this is U big G, call that little g, U C for Coulomb potential as 1 over 4 pi epsilon naught Q1 Q2 over R. Now these are scalars, remember. Okay, these are scalars. I have the potential due to a spring, U equals 1/2 spring, K S squared, where S is the amount it's stretched or compressed. Yeah, so those are some that you're going to see. Okay, and now one other thing. What if the force is not constant? Because this does not have constant force, not a constant force, not a constant force. If that's the case, then actually we would say work equals the integral from point 1 to 2 of f dot dr. You'd have to integrate. And it can get complicated. But that also means that the potential is actually defined as not negative work, but negative from point 1 to 2 of f dot dr, because it's the opposite of the work, and that is important. Now you can also go back the other way, because remember that an integral is an opposite of a derivative. So that means if I know the potential, I can find the force. But the force is a vector and the potential is a scalar. So it actually looks like this. The force in the x direction is negative the derivative of the potential with respect to x. And then you could do the same thing for y and z. Okay, so I think that's good enough for now as an introduction to work energy principle, or reminder of work energy principle. And hopefully we can move on from there.